check out our website, Armchair History TV, for exclusive history videos, like our latest on the 7 Years' War. In fact, that episode is just one part of a full series covering the entire war. So if you want to be there to watch the full completed series, be sure to subscribe to our platform so you don't miss it or the countless other videos that we and other historical content creators release every single week. Use code ARMCHAIR75 for 75% off of your first month. A blinding flash and a roaring fireball blasted into the desert sky of New Mexico. The shockwave lit the nearby mountains in a startling array of light and color. Off in the distance, scientists and military personnel witnessed the Trinity test, the first nuclear fission detonation in history, on July 16, 1945. Kenneth Bainbridge, the test's director, described the moments after the explosion. "Finally, I could remove the goggles and watch the ball of fire rise rapidly. It was surrounded by a huge cloud of transparent purplish air produced in part by the radiations from the bomb and its fission products. No one who saw it could forget it. A foul and awesome display." The Manhattan Project team nicknamed the bomb Gadget and proved that a plutonium fission detonation was possible without burning up the entirety of Earth's atmosphere. Conceived as a powerful new weapon, the atomic bomb's incredible and terrifying potential changed the course of human history. However, nuclear technology was not only imagined as part of weapons development. Scientists had studied nuclear energy and radiation for almost a century before the Trinity test. By the 1930s, scientists realized it was possible to harness atomic fission. On December 2, 1942, in a basement lab at the University of Chicago, Enrico Fermi started Chicago Pile 1. This reactor demonstrated the first successful use of nuclear fission to generate electricity. Scientists viewed nuclear technology as both a source of energy and a vector for destruction during the mid-20th century. Its military use, nevertheless, dominates its public perception. Fear of nuclear annihilation has led to mass political movements against nuclear technology in any form. Its civilian usage is often underappreciated, however. Nuclear technology is a common, even crucial aspect of improving people's lives. By the late 19th century, scientists began discovering elements unknown on Dmitry Mendeleev's periodic table. However, scientists noted that some elements, such as uranium and thorium, generated strange forms of energy. Scientists Wilhelm Röntgen and Henri Becquerel found that uranium could produce X-rays, a type of light that could move through objects. Becquerel accidentally discovered nuclear radioactivity and differentiated it from X-rays, realizing that uranium could interact with a photographic plate at a distance through opaque paper, and it could not be repelled by a magnetic field. Polish-French scientist Maria Skłodowska-Curie furthered Becquerel's work, identifying and naming nuclear decay as the theory of radioactivity. Radiation was a breakdown of elements into fragments, which released energy and particles. She also discovered new elements, such as polonium, a decayed form of uranium. In 1903, Madame Curie won the Nobel Prize in Physics for discovering that some elements, like uranium and thorium, produced this natural radiation. The dawn of the 20th century proved to be a period of exponential growth and advancement in the study of nuclear energy. Scientists of this era focused on nuclear fission and fusion research. Frederick Soddy was the first to observe a form of radioactivity called alpha decay, with the discovery being published in 1902. This guided Soddy in 1913 to discover isotopes. These were elements that could gain or lose neutrons and thus change atomic weight but remain the same element. In 1919, Rutherford accomplished the first artificial nuclear reaction. Other scientists, including Leo Szilard and Lise Meitner, theorized that uranium isotopes were fissile and could create a powerful chain reaction, releasing tremendous amounts of energy. Szilard and Enrico Fermi realized that uranium-235 fuel could produce a fission chain reaction. To prove this, Fermi built and tested the first fission reactor, using a controlled chain reaction to stabilize the propagation of energy. The experiment was a success, but with it came the true concern. Contrary to the controlled conditions of a reactor, all it took to weaponize this energy was to remove any limitations and allow for total self-propagating and sustaining reactions, in effect, creating an atomic bomb. Some physicists in the mid-20th century realized the enormous military potential of nuclear weapons. One single bomb had the potential to replicate the damage of thousands of conventional bombs. In 1939, Szilard and Fermi enlisted renowned physicist Albert Einstein to write to President Franklin D. Roosevelt, urging for the nation to pursue nuclear fission research. Recognizing its significance, the United States raced to develop nuclear weapons, fearing Germany might succeed first. The US assembled its top physicists, many of whom were refugees or immigrants, under the Manhattan Project, and placed them in the New Mexico desert to expedite atomic weapon testing and development. At Los Alamos, scientists and engineers working under J. Robert Oppenheimer studied challenges to the technical problems of weaponizing nuclear fission, with physicists like Chien-Shiung Wu, who created improved Geiger counters and developed a method to enrich uranium in large quantities. Altogether, their efforts culminated in the 1945 Trinity test. With the test's success, the US War Department and State Department ordered the use of atomic bombs on Japanese cities. Planners hoped that the atomic bomb's power and the terror of further destruction would force the Japanese government to accept surrender. US leaders hoped to avoid taking massive casualties in their planned conventional invasion of the Japanese home islands. US Secretary of War Henry Stimson argued that American forces would incur 1 million casualties during the course of a ground invasion, while Japanese losses could have matched American losses. Since 1945, scholars have debated whether dropping atomic bombs was necessary or moral. Some questioned President Harry S. Truman's commitment to unconditional surrender. Perhaps offering conditional surrender to Imperial Japan may have ended the war without using atomic weapons. Japan was close to defeat and would have accepted surrender, considering the looming Soviet invasion of Japanese-occupied Manchuria. But others point to Truman's use of the bombs as a power play to limit the Soviets' interests in East Asia. Moral questions also surrounded the use of atomic weaponry, specifically its use on civilian populations and its long-lasting after-effects. Given the alternatives, some scholars and the American public thought that bombing Hiroshima and Nagasaki was immoral. From the traditional perspective, if the atomic bombs could end the war quickly, they had to be used on significant targets. American military leaders created a list of Japanese cities that had some form of military value. Targeting cities for nuclear bombardment was a natural extension of the aerial bombing campaign that the US already conducted. After President Harry S. Truman issued the Potsdam Proclamation on July 26, 1945, USAAF B-29s dropped the Little Boy and Fat Man atomic bombs above Hiroshima and Nagasaki in August 1945. The explosions released the energy equivalents of 15 to 20 kilotons of TNT, creating temperatures on the ground that reached over 3,871 degrees Celsius or 5,199 degrees Fahrenheit. This heat incinerated everything within a close radius. Humans and animals were vaporized, while buildings melted or fused to the earth itself. The blasts generated shockwaves that flattened structures within a radius of 12 square kilometers, or 7.5 miles, demolishing infrastructure. Approximately 150,000 to 240,000 people died. Nuclear bombs kill in the same way that conventional bombs do: concussive force and heat, except on a much larger scale. The added tragedy of the atomic bombing of Hiroshima and Nagasaki was the increased rate of radiation poisoning. For decades afterwards, tens of thousands more would die of exposure to the bombings, whether through radiation poisoning or elevated rates of leukemia. Japan surrendered shortly after the second bomb fell. For its part, the US government suppressed images and films of the loss of life and destruction for 30 years. The United States nuclear weapons monopoly was short-lived. Soon after the bombing of Japanese cities, the Soviet Union sought to rush development of nuclear weaponry in the hopes of catching up with the United States. Through the use of its scientific program facility, Artemis-16, Soviet scientists developed and tested a nuclear weapon on August 29, 1949. Soviet spies at Los Alamos and in the West provided crucial intelligence that helped Soviet scientists speed up the technical aspects of turning a nuclear fission device into a bomb. Knowledge of nuclear weaponization spread during the Cold War, with several other nations establishing their own arsenals. The United Kingdom was able to draw from its involvement in the Manhattan Project, testing its first atomic bomb in 1952, and becoming the third country to develop and test nuclear weapons. From 1960 to the 1990s, a host of other countries would follow. For nearly 50 years, the world lived under the shadow of mutually assured nuclear destruction. During this period, the nuclear superpowers conducted over 2,000 live weapon tests on more powerful bombs. Nuclear weapons testing, however, had terrible consequences. Repeated testing displaced indigenous populations in the Marshall Islands and in northern Russia. The fallout made their homes uninhabitable. Those who once lived there or near testing sites suffered crippling radiation exposure, and multiple generations have been afflicted by higher rates of cancer. Despite the dangers of fallout, the most powerful of these demonstrated included testing hydrogen bombs. Hydrogen bombs, also known as thermonuclear weapons, relied on nuclear fusion rather than fission. On October 30th, 1961, the USSR tested the Tsar Bomba, the largest nuclear explosion in history. The Bomba was a thermonuclear fusion bomb, 1,570 times more powerful than the bombs dropped on Hiroshima and Nagasaki combined. Test results demonstrated destruction on a massive scale. Buildings some 30 miles or 48 kilometers away were leveled. Windows broke in Norway hundreds of miles away, and aftershocks produced earthquakes. H-bombs had the potential to wipe out entire metropolitan areas, killing millions of people. A wide range of nuclear weapon systems seemed poised to revolutionize the atomic battlefield. 3 systems formed the nuclear triad: long-range heavy bombers, nuclear missile-carrying submarines, and land-based missiles. Cold War superpowers designated and tested intercontinental ballistic missiles, otherwise known as ICBMs, to reach their targets and deter each other from attacking. The space race, ostensibly to explore outer space and land humans on the moon, was a lightly coded contest to prove which superpower would engineer more sophisticated and accurate ICBMs. It was an attempt for the US to catch up to the USSR's efforts and bridge the supposed missile gap between them. Outside science and engineering, ICBMs became a crucial part of the diplomatic jockeying between the US and the USSR. The placement of nuclear-armed missiles meant to check the other superpowers' interests was typical of the period. The race to field more numerous and destructive nuclear weapons reached its zenith during the 1980s, slowed only when the US and USSR signed the SALT, START, and SORT treaties to reduce the number of weapons each nation held. The threat of nuclear war remains, as the major nuclear powers still have thousands of nuclear warheads in storage and at the ready. Some scholars have proposed that nuclear weapon deterrence has created an atomic peace in which the most militarily capable powers of the world do not directly engage in warfare with one another for fear of mutually assured destruction. Others contend that humanity should not rely upon the assumption that everyone fears mutually assured destruction. Others contend that humanity should not rely upon the assumption that everyone fears mutually assured destruction, and that countries should look to disarmament as the best guarantor of peace and safety. Terrorism and rogue states further complicate the concept of atomic peace. Nuclear power is the other side of nuclear technology's potential. The US Navy recognized the efficiency of nuclear energy, equipping its carriers and submarines with nuclear reactors. Thanks to its power output, it was possible to operate these vessels for long-running missions without concern for frequent refueling. Notably, the US Navy has maintained a nearly impeccable safety record with its nuclear fleet, having never experienced a nuclear meltdown. Successes in the military inspired civilian applications. Throughout the 1970s and 80s, countries with nuclear capabilities constructed reactors capable of generating abundant electricity without the need of fossil fuels. Reactors use carefully controlled fission reactions to release heat and boil water. The resulting steam turns turbine blades that generate electricity. Radioactive fuel used to produce electricity in small quantity, and the steam released is harmless to the environment. Though radioactive fuel can pose a threat to people and the environment if not managed properly. Nuclear power is controversial nonetheless. Human error, faulty design, and natural disasters have led to catastrophic meltdowns. A meltdown occurs when the radioactive fuel is not sufficiently cooled and the core overheats. The extreme heat bursts through the containment cells and into the surrounding region, spewing radioactive material for hundreds of kilometers. Acute radiation poisoning can cause rapid death or later onset cancer. Hundreds of thousands or millions could die. At Chernobyl, the reactor meltdown forced hundreds of thousands of people in northern Ukraine to flee their homes permanently, while potentially tens of thousands died trying to contain the fallout. To this day, the exclusion zone serves as a stark reminder of the lasting damage that peaceful nuclear technology can cause. Because nuclear contamination is so severe, its impact can last for thousands of years. Major political movements of the 1980s and 90s called for the end of nuclear weapons and nuclear power due to the threat of radiation exposure. Though reactor operators learned lessons from failure, fears about potential meltdowns and fallout remain. In 2011, the earthquake and subsequent tsunami along the east coast of Japan damaged the Fukushima nuclear power plant and released tons of radioactive material into the surrounding region. Cleanup efforts are still ongoing, and there are debates about whether the benefits of nuclear power outweigh the risks. Despite the fears of possible meltdowns and radiation poisoning, nuclear technology is of vital importance in the medical, scientific research, and engineering fields. Medicine, in particular, has benefited from advances in nuclear science. When nuclear research was only decades old, X-rays and radiation imaging revolutionized medicine, giving doctors a non-invasive interior view of the human body. During the First World War, Madame Curie advocated for the use of X-ray machines in portable units. These machines would be supplied to military hospitals close to the front so that doctors treating wounded soldiers could identify injuries in detail never before achieved. From the advent of X-ray technology in the First World War, medical researchers have developed new uses for nuclear technology that have revolutionized cancer treatment. But there are many other fields of study that incorporate nuclear innovations, from the use of gamma rays to test the integrity of infrastructure to using radiocarbon dating to piece together our human evolutionary origins. Humanity's future scientific advancements depend on nuclear energy's continued study and development in the face of future possibilities and hazards. Nuclear technology has tremendous potential to destroy life on Earth, improve human life, and solve humanity's most pressing challenges. The total destruction and terrible loss of life at Hiroshima and Nagasaki is a stark reminder of nuclear technology's potential force for devastation. While atomic weapon testing's destructive capabilities are not as readily remembered, they too caused great harm. Like any technology, it relies on its users' values and good intentions. In many ways, the threat and promise of nuclear technology is reflected in the words of Leo Szilard. Great power imposes the obligation of exercising restraint, and we did not live up to this obligation. This video was produced and created in collaboration with OER Project. For more information on how OER Project offers free, comprehensive, and fully supported social studies curricula for middle and high school teachers and their students, click the link in the description.